Question 9. Monochromatic light of wavelength 500 nanometers falls on a metal cathode of area 2000 millimeters squared and liberates photoelectrons. The light intensity at the surface of the metal is 1.0 times 10 to the minus 2 watts per meter squared. Calculate the frequency of the light. So we're going to start from V is equal to F lambda again. F is V over lambda, which is 3.0 times 10 to the 8 meters per second over 500 times 10 to the minus 9. That means we can calculate the frequency, and it's 6.0 times 10 to the 14 hertz. The energy of a single photon of light, so we know E is equal to HF, or is equal to HC over lambda. We can use either. Let's use HF, so 6.63 times 10 to the minus 34 multiplied by 6.0 times 10 to the 14, which gives me a value of 3.98 times 10 to the minus 19 joules. Or if I want to calculate it in electron volts, I divide by 1.6 times 10 to the minus 19, so that gives me 2.49 electron volts. The number of photons falling on 1 square millimeter of the metal in 1 second. So we might say that the number of photons is equal to the total energy divided by the energy of 1 photon. So the total energy we can see in 1 second. So effectively in 1 second the watt and the joule are the same thing, because the watt's the number of joules per second. So this light is delivering 1.0 times 10 to the minus 2 joules every second, but that's in a meter squared. So to work out the amount in 1 millimeter squared, I'm going to have to take that intensity and multiply it by the size of the area, and then the energy of 1 photon we know is just equal to HF. So the intensity is 1.0 times 10 to the minus 2 multiplied by the area of 1 millimeter squared, so 1 times 10 to the minus 3 squared, divided by the photon energy, but we worked that out already up here, so we don't need to do that again. 3.98 times 10 to the minus 19 joules, which tells me there are 2.5 times 10 to the 10 photons arriving at each square millimeter per second. The total photoelectric current, assuming that each photon releases 1 photoelectron, so the I is Q over T. So we're going to continue working in 1 second all the time as we go through. Each square millimeter has this many photons arriving at it. The area of our plate is 2000 square millimeters, so we need to do the number of photoelectrons in 1 square millimeter multiplied by the 2000 square millimeters that we have, multiplied by the charge of each photoelectron, and that's happening in 1 second. So that gives me a value of the current of 8.04 times 10 to the minus 6 amps, or we could write 8.0, I think probably 2 significant figures based on what we've done, milliamps.